Hello and welcome to this video titled Exploring Wave Patterns with Compressed Mylar, a fantastic science fair project. In this video I will demonstrate a cool phenomenon discovered by Lee Guthrie. This experiment shows how Mylar film forms stable, wave-like patterns under compression, a little known but visually stunning effect. This is a phenomenal macroscopic example of quantum jumps. This is a perfect analogy for how an atom changes energy levels when its electron absorbs or emits a photon and shifts to a new eigenstate. It's also a fantastic science fair project.
For this demo, we're using a wooden mechanical vise and a strip of DuPont Mylar, a durable, elastic material. The Mylar is clamped at both ends to form a preset wave shape. A full explanation of how to recreate this experiment comes later in the video.
As we apply compression with the top plate, the material cannot flatten completely. Instead, it forms more wave patterns, jumping from one energy state to another. Each added half wavelength represents a higher energy state in this macroscopic analogy of quantum jumps. Watch how the wave shape transforms as we increase the compression, illustrating the stepwise change in energy level. As the pressure decreases, the energy is released in discrete jumps, similar to quantum jumps in atoms. Adding energy increases the wave's nodes, while removing energy reduces them, just like electron transitions in atoms.
Next, I want to explore one of the most quintessential problems in quantum mechanics, the particle in a box. This is the simplest example where we can apply the Schrödinger equation and see how quantum mechanics works in a simple system that can be produced in the laboratory. This applet demonstrates the classical particle in a box problem. It shows the wave function as well as the square of the wave function, which is the probability density. The wave function represents the quantum energy state of the electron, while the square gives the probability of finding the electron at a specific location. The applet does not include time dependence for the wave function. A key concept in quantum mechanics is the quantum jump, where an electron absorbs a photon and transitions to a higher energy level. E1 is the ground state energy. This is the lowest energy of the system. This is the wave function for the ground state energy. The next allowed energy state is E2. E2 takes on this pattern. The energy value E2 is equal to 4 times E1. E3 has 3 antinodes, and the energy E3 is equal to 9 times E1. This is the energy level 4 corresponding to this wave function, and it's equal to 16 times E1. When an electron absorbs a photon, it can jump from one energy level to another. When the electron is in an excited state, it can release a photon and drop back down to a lower energy state.
The quantum mechanics of a particle in a box tells us how a very tiny particle behaves when confined to a small space. For the particle in a box, the energy levels spread farther apart as the quantum number n increases.
The original experiment was conducted in an engineering lab using a steel plate and a hydraulic press to study its load deflection response. The applied force and resulting deflection were continuously measured. At certain points, the force dropped abruptly, signaling a phase transition in the plate's behavior from one deformation mode to another, absorbing the force through snap-through motion.
This graph shows the load versus deflection for a steel plate under increasing force. As the applied force increases, the steel plate undergoes abrupt transitions at specific points.
The y-axis is the load produced by the hydraulic press. This is measured in pounds. Each one of these 4 locations on the red curve corresponds to a crest in the plate's deformation, followed by a sudden drop in force. We'll call this a snap-through event, where the plate quickly shifts between energy states.
I prefer to call it a quantum jump.
The first deflection, where it went from one antinode to 2 antinodes, which did behave a little bit differently, required about 225 pounds of force. The load for the second deflection is about 4 times higher than the initial deflection force. The third deflection happens at roughly 9 times the initial deflection force. This follows the same pattern as the energy states of a particle in a box, where the energy levels are proportional to the square of the quantum number. You can recreate this experiment cost-effectively using Mylar film, which behaves similarly under lower forces.
Hands-on quantum. Make a macroscopic spring.
Oh, wow.
Very simple to make. This one was made out of wood. Aluminum angle irons here to clamp the material in. The material is Mylar. It's fairly cheap. This white material was about 11 thousandths of an inch thick. The press I have here has two threaded rods to guide the upper section of the press that applies the force onto the top of the crest of the wave. So this setup would be something you could easily make and use as a science project. Angle is around 30 degrees. We've got this set on 30 degrees. So as a rule of thumb, you've probably got a buckle that's the correct height for your process to work.
A project on macroscopic quantum jumps could be a fantastic science fair research project. As an example of one advanced variation you could make to this experiment, you could change the surface from flat to step shape and observe the wavelength difference above and below the step. Here are a few other potential follow-up experiments that can be performed.
Acephysics.org, Math and Physics Tutoring with Dr. Hudis.